Hello all. We got a pretty interesting question to tackle today, so I'm going to go ahead and start on it. The statement reads, is Ampere's law consistent with the general rule that divergence of curl is always zero? Show that Ampere's law cannot be valid in general outside of magnetostatics. Is there any such deficit in the other three Maxwell equations? So that's a good thing to consider moving forward and how you approach these equations. The solution to this is that Ampere's law says that del cross B is equal to mu naught J. Now, if we put this together with the continuity equation and we take the divergence of both sides, we see that we end up, we're able to move mu naught out since it's a scalar. And we see that del dot J is just the continuity equation, negative partial rho divided by partial T. But realize that in magnetostatics that this is okay because rho is a constant. We said that the charge or the movement of charge, the current of charge is steady. So it's not varying in time. So since it's steady, the partial with respect to time goes to zero, and it's okay to work here. But in general, this shows that it can't work unless rho is steady. So moving to the other equations, with the electric field, we know that del cross E is equal to zero, so taking the divergence of both sides yields del dot zero vector, which is still zero. So that one's okay. And the other two equations deal with divergence themselves, so there's no relevant vanishing second derivative outside of the one we just worked with, which is the curl of a gradient is zero, and that's shown in this equation already. So we're good to go on the other ones. But nonetheless, an interesting concept to consider moving forward when we take for granted these static cases that we use to solve these problems. Good insight.